So what happens at the top of the loop? You always need to be careful at the top of these loops because orientation matters. This is an inverted loop, so we want to make sure we draw the pilot upside down. They're not always going to be inverted, so you have to be careful to make sure our forces are the right way. So upside down, pilot right here. We're going to do the same approach. Sum F equal FC, and we'll use mv squared over r again. Now, let's sum the forces. Do the same kind of thing. mg down. Now let's be careful here. Everybody likes to have n pointing upward because you're used to it. The normal force is not up. The chair is not pulling up on the pilot. That would be the equivalent of you trying to sit on the ceiling and being able to sit there because, well, the ceiling's pulling up on you. I've tried that. It doesn't work. I've landed on my head, which probably answers a few questions about myself. Anyway, look at how the seat is. If you sit on a chair, the chair pushes back on you and is down. So in this case, both help supply the centripetal force. N and gravity help. So what does that mean? N doesn't have to be as large, and interesting things happen. So this is the answer to the problem, and you could start putting in numbers, but let's carry it out. The normal force now is mv squared over r minus mg. Factor out an m. V squared over r minus g. Or m ac minus g. So we want to analyze what happens in parentheses this time. Before we do that, just so you know, this is the place of minimum force. We really don't care about the minimum force. If you think about a trick going around in a circle, sometimes it's easier to think of maybe a bucket of water at the end of a string, which we've seen before. There really are two places we care about. The bottom, will the rope break? We analyze that. And at the top, we want to make sure the water doesn't fall out of the bucket. So this is what we're looking at, because the force is a minimum up there. So if we don't want the water to fall out of the bucket, there's probably a certain speed needed for the trick to work. Well, we can analyze it by looking at the minimum force. For the trick to just barely succeed, for it to barely make it, what literally is going to happen is N is 0 for the pilot to just make it. Or in this case, gravity is the only thing keeping the person in a circle. A lot of roller coasters are made this way. When N is 0, the only force keeping the person or keeping the roller coaster moving in that circular path is gravity. So if N is 0, what ends up happening is this. AC equals G. And when these two equal each other, this is how you can find the minimum speed needed. How does that work? Well, let's just think. If AC is V squared over R equals G, well, in this case, V is root RG. That's the minimum speed needed for the trick to succeed. Any speed lower than that, and the pilot's not going to make it. And that might cause problems because that might mean the engine will stall. And that causes even more problems. So we use the bottom of the loop to figure out the maximum force. The top of the loop is where minimum force occurs, and we usually use it to determine the minimum speed needed for the trick to succeed. And in this case, when AC equals G, what's really interesting is the pilot is weightless at the top of the loop. At the top, when AC equals G. This is one technique that is used to give a couple extra seconds of weightlessness for astronauts in training. Anytime you can get a little bit of extra weightlessness training, it helps out to see how people can actually respond to it. And when you don't get a lot of time all at once, 2 seconds is a considerable amount of time added on to whatever else you have as you're practicing being an astronaut.